Thanks so much, and thanks for sticking around. Sorry for these technical difficulties. But if you want to ask questions in French, that's totally fine. I do understand French. I'm just not very competent in speaking, so I decided to do this in English. So I'm from EPFL. Here's a picture of our campus. We have a very nice setting. And today I want to talk about different things. This is my current team, and these are some of the areas that we work on, and what that all means will become hopefully clear throughout the talk. Today I'm only going to touch upon two things in the area of computational caustics and smart materials, and show you examples on how these things can be used also at the architectural scale. But just to mention this, we also work on complex assemblies. Here are some projects, and in particular I'm interested in sort of a full-scale closed-loop robotic assembly and construction and architecture. So these are some pictures from a large project that is hosted in Zurich, the NCCR on digital fabrication and architecture, where we want to use robotics and computational design to build and assemble complex structures. So if you're interested in that, I can tell you a little bit more about this afterwards. We also work on all areas of computational design. Again, I'm not going to show these type of projects, but what I'm going to talk about today, of course, contains a lot of aspects of computational design. And I want to mention one of our previous work because it plays a role in this talk. This is some older work we did in computer animation, but the idea was really to have a robust simulation method that can allow us to simulate a lot of different physical phenomena. And if you're interested in this, there's a free source code version available. But what's probably more relevant, especially in architecture, is that we worked on this with Daniel Piker, who some of you might know. And in fact, it's that technology that came into the new version of Kangaroo. So Kangaroo 2 uses our Projective Dynamics approach. And for those of you who've played with it, I think it's a very, very nice tool. So you will see this reference a lot in the talk because that's the underlying computational engine that we use for many of our things. But let's get started with the actual presentation. So today I want to talk about light, matter, and form, and this is deliberately very generic. So let's start with matter and form. The first project or class of projects I want to talk to you about has to do with what we call, or many other people call, Auxetic Materials. And this project literally started when I found this object in a design store. It's a piece of metal, and it has these incisions inside, and these incisions allow you to deform it in interesting ways. And I was quite intrigued to figure out, what can you create with such a structure? Auxetic materials are used in various forms, and the peculiar property of an auxetic material is that if you stretch it in one direction, it expands in the other. Most normal material, like if you take a piece of rubber or a piece of metal, if you would stretch it, it would compress in the other direction. But auxetic materials expand uniformly. And they're used for various kinds of applications. The last one is a very futuristic one, which of course doesn't exist. So our question was, what can we do with these materials? So we first actually made a bit of that type of material. And what you really have here is an inextensible sheet, in this case a piece of plastic, that becomes stretchable by introducing these cuts. And when you look at this, you can observe that the material actually scales isotropically. So these openings that form, they open uniformly and isotropically, meaning in all directions equally. And that's something that we can map to mathematical theory. So I'm not going to go into too much detail, but I want to mention that there is a large class of differential geometry that deals with so-called conformal deformations. Conformal deformations illustrated here are the ones where if you deform the object, it only scales uniformly, locally, or rotates. So each of those little squares has scaled up or down in size uniformly and has been rotated. So there's no shearing going on, and this is a particular class of deformations. The important point here is that with this observation of linking this material to that mathematical theory, we can actually analyze the type of geometries that become feasible. So in particular, if you take a sheet of metal or a sheet of plastic, you can typically only realize these developable surfaces. And I've seen a great prototype outside from Nicola that you probably also have seen that works with these type of developable structures. But if you go to the domain of non-developable, meaning anticlastic or generally non-zero Gaussian curvature surfaces, this becomes possible if you have a material that can actually also stretch. Right? And it's actually necessary that the material stretches. If it cannot stretch, you cannot have double curved surfaces. Now, fortunately, if you are in this domain, and this is, I think, almost the only equation I will show today, where you're dealing with conformal geometry, the type of geometry that is induced by the specific material structure that I'm looking at, there is a relatively, at least simple-looking relationship between the curvature of your surface and the scale factor, meaning the amount of stretching. And in particular, what's important is, this is the Laplace operator, it's a second derivative operator. It essentially measures the variation of scaling. So if everything would scale at the same rate, your surface would stay in the plane. It will not deform out of plane. But if you have variation in scaling, then you can reach interesting curved shapes. So we have a relationship, a mathematical relationship, that allows us to study the type of surfaces that can be realized. There's something special in our material, which the theory does not capture, and that is the fact that our material cannot expand arbitrarily. Right? It's limited in the amount of scaling. In particular, the area can only increase up to a factor of 4, or in length, that's the scaling factor that we measure here, it must be between 1 and 2. So the question is, what kind of surfaces can be realized? And that's something we want to study in more detail. I'll show you one example to give you some intuition. What about the sphere? Can we model a sphere out of a flat sheet of material of this type of auxetic structure? Now, in order to study that, we need to find a mapping of the sphere into the plane that is conformal. Okay? And the specific one is reached via stereographic projection. So the details are not so important. I'll show it to you in a 1D example. If you take a sphere and you project it onto the plane, then this is basically a projection, in this case, through the North Pole. And what you can see is that if you take this piece of material and you map it onto the sphere, it's been increased in area, right? It's becoming bigger. In particular, it has been stretched by a factor of 2 at the South Pole. If you're at the equator, the stretch is actually 1. There's no stretching going on. And if you're in the upper hemisphere, you would have to compress the material, right? Now, we know that our maximal and minimal stretching have to be between 1 and 2. And that, with a little bit more analysis, proves that you can at most do half a sphere. Okay? And here you see a realization. In this example, the material is fully expanded at the pole and fully compressed, meaning completely closed, as in the original state, at the equator. So that's, if you would try to make a sphere, you would fail, right? It's not possible. You can prove it, right? So that's sort of an example that shows if you do some analysis, you can avoid trying to do things that are impossible. So that's, in some sense, restrictive, but the story is actually not so bad. There's more theory that we can leverage. If we're given an arbitrary shape, and this is a geometric model of Max Planck, then there's a theorem that says there's always going to be a conformal map with some constraints, but this is what it looks like. I can flatten this three-dimensional shape into the plane in such a way that each triangle is only scaled uniformly. There's no shearing going on here, right? So that's nice. That basically suggests I can do pretty much anything, except that, of course, the scaling factor is not bound by the restrictions imposed by the material, right? So this one I could not realize physically with my material because it needs to stretch more than the material can tolerate. So what can you do? Well, there's a trick, and I'm not going to go too much into the details, but it's basically to say you have to cut your surface open. You have to introduce so-called cone singularities, and then this one you have to cut open until this cone singularity lies on the boundary of the model. And once you do that, you can reduce the metric distortion to a point where your scaling is below a factor of 2. And now that means this is actually a model I can realize, and I'll show you an example later. So how do you turn that kind of theoretical analysis into an algorithm. The idea is basically to do post-rationalization, if you will. You start with a design surface, and you want to figure out, can I build this? And how would I need to build this? And the first step, and that's absolutely crucial, is to compute this conformal map. There's established algorithms in geometry to do that, which might need to introduce these type of singularities. And then you have to run an additional optimization to find the actual layout of the material on the surface. And the way to do that is using, this is sort of the typical thing we always do, some geometric, some physical energies. So this is kind of a variational approach. And this type of optimization falls directly into this framework that I briefly mentioned and didn't explain. So we basically use our library. There's nothing much to invent here. This is basically standard stuff. But the key point is that, if you have such an optimization, why not just let it run on the model directly? Why do you need this intermediate step? It's absolutely crucial because this is a highly nonlinear, non-convex energy. If you would just try to do this naively, let's say, you initialize it with a planar piece, and this is what you might want to do physically, right? You might want to take your material and sort of wrap it around the surface. If you let this run, then you get something like that. You basically get stuck in a really bad local minimum, right? But with the conformal map, you actually find the structure and mapping of the 2D material, and now you can just cut that out of a piece of physical material, and you can then actually deform that material into the surface. So I have this model here. I can show it to you. Well, actually, maybe you can come up afterwards if you want to have a close look. So this is basically the space mask. And what you see, and I think I have a little video as well, makes it easier to see. What you see is that the openings of the structure varies across the surface in a way that is actually quite hard to predict. At some parts it's completely closed, in other parts it's completely open. At the tip of the nose is our singularity, right? So here you actually have a cut. You can see it if you look closely because we didn't stitch it nicely together, but in principle it would fit perfectly. Here's another example of a shoe. Not a very comfortable shoe, it's laser cut out of aluminum. But the point is there's no seam, right? The material is connected somewhere here, but you don't see it because the optimization makes sure it fits perfectly. And this is something that, if you look at clothing, for example, if you have a pattern, they never fit, right? If you have an arm, the pattern is never continuous because they haven't been optimized in that way. Another fashion example, we get to architecture a little bit later. Again, you get a seamless mapping. This is the 2D layout. So this thing connects to that. This blue curve connects here in a seamless way. And you've globally optimized the structure to fit perfectly. So these materials are actually quite versatile. They allow you to approximate interesting shapes, but you need to have the right computational approach, right? So this is, in essence, the main message of this entire talk. If you try to do this in a naive way, in a direct sort of, black box optimization kind of way, it's very hard. So now I want to show you something that we did with that, and that relates back to an interest I had for a long time in this idea of deployable or shape morphing structures, which are used for various kinds of applications, basically geometric structures that can transform from one state to another, or maybe have multiple interesting geometric states. So if you look at these type of examples, what's common to all of them is that they're dealing with very simple geometries, planes, cylinders, spheres, and so on. Because the deployment makes things, of course, much more complicated. Right? Now you're not just trying to fabricate one final shape, but you're trying to fabricate a mechanism that can transform from one shape into another. So we wanted to look at that, but transcend from these very simple geometries to a richer space of shapes. And see if we can go to something more freeform. But we wanted to do that in a way that retains the simplicity of fabrication. We didn't want something that's very complicated to build, and also is simple to deploy. We didn't want something that has to have, tons of controls and motors and things like that. And we're going to leverage our 2D auxetic material again. And for the deployment, we look at something very simple, namely inflation or gravity. Okay? And the key property here is that we're actually designing a material, if you will, or the structure, such that in the 2D state, it already knows about which shape it wants to go to. And I'll show you what that means in a second. And again, this is based on this notion of conformal geometry. So here's the example we've seen before. I can make a sphere, and in order to get curvature, I need to have varying openings, right? I cannot have the same opening everywhere. It needs to change across the surface. But the problem is, if you want to take the flat material and deform it into this shape, you'd have to know exactly how much you need to open everywhere. Right? And that's kind of hard to do. Here's another variant. In this example, the model is fully opened everywhere. I've stretched the material until I cannot stretch it anymore. And it actually defines the target shape. So the material is expanded everywhere, which means that if I have some mechanism that just expands my material until it can't expand anymore, you get to the shape you want. Now, what's the difference between the two? Here, these blue triangles are all the same, and the openings are different. Here, everything is fully opened, but the triangles are not the same anymore. So if you look at this in the undeformed 2D state, it actually looks like that. So this material is programmed towards this shape once you maximally expand it. Okay? And that's actually retaining the simplicity of fabrication, because we laser cut these things anyway. Right? Who cares whether we cut a perfectly regular pattern or this type of pattern? But what it means is that you now have something that, you could say is a smart material. It changes in the way it deforms across the surface. So we can now very precisely control how much scaling we allow. If we start with something that looks like this in the flat domain, it cannot stretch anymore. We have a scale factor of 1. If we start with something with large triangles but very close together, we can stretch it up to a factor of 4 in area or 2 in length. Okay? So that's sort of the optimization we do now to encode where the model wants to go once we deploy it. So how do we deploy? Well, let's look at inflation. We're also going to look at gravity. So the idea is now, in order to get the shape to the form that we want, we need to stretch the material. And inflation is a good way to stretch material. But then the question becomes, which shapes can be inflated? Okay, so if you look at this type of example, this is a sphere with just a bump. If you pump in air, this will never be a stable state of an inflated surface, because it can increase in volume without increasing in surface area. The bump would just plop out. Right? So this sort of intuitive argument is actually something you can make much more formal. This one has negative mean curvature. Now we're talking about mean curvature, which is the sum of the two principal curvatures. And this one, on the other hand, has positive mean curvature everywhere. So that's just the formal definition of mean curvature. But what we've proven is basically that if you want to inflate something and get to a stable state, your surface must have positive mean curvature everywhere. So again, we have a classification, and it's not clear what that means, right? It's just an abstract mathematical statement. A sphere has positive mean curvature everywhere. That's okay, but what other shapes are possible? But the point is that if you give me a shape, I can immediately tell you whether this is realizable or not. And if it's not, like for example this model here, because it has again such sort of invert bump, then we can modify it to become a positive mean curvature surface. So again, this is a typical, fairly standard geometry processing optimization. Here's another example, and how we modify it. And interestingly, positive mean curvature doesn't mean you cannot have negative Gaussian curvature. Right? Here you have saddle points on the surface. It doesn't mean it has to be spherical or like a blob. I guess this is a blob. But the space is actually quite interesting. And then we can realize it with our auxetic material. Here are some other examples of surfaces you can realize. But again, the message is that if you design something arbitrary, chances are very small that it would fit into that class of surfaces. Okay, so you need to understand the geometry behind the material and the deployment process in this case. Now, the algorithm is quite a bit more involved. I'm not going to go into too much detail here, but the structure is actually somewhat similar. The first step is, again, a conformal map, flattening your input surface into the 2D domain. Your material is flat, right? That's sort of one thing that makes fabrication simple. We're fabricating the whole thing in 2D. You can laser cut it, you could also 3D print it, you can assemble it. I'll show you some examples later. And then we lift that 2D material onto the surface and do a joint 3D and 2D optimization. Now we have to optimize the material itself, right? Before we just had this, a regular pattern, but now we need to find the actual pattern corresponding to our target surface. So the last part is the optimization. And again, we use the same solver. We only have one tool. We always apply it. To be precise, this is a very general framework in which you can implement different types of numerical optimizations. So there's a little bit of adaptation going on. So let me show you an example. Here's this model. So we've laser cut it, and we built a little support frame so we can inflate it, and we put a balloon onto that frame, right? And if you inflate the balloon goes wherever it wants to go. I mean, you could inflate it more at some point, it would just pop. But there's no clearly defined shape for it. And then we mount our material on top of it. And now if you inflate the whole thing, then our material constrains the balloon to go only so far until the material is fully expanded, until all these hexagons are fully opened. Right? So this 2D flat material knows this shape. The balloon doesn't. Right? So that's the whole point. So deployment is easy. Right? You don't have to control the pressure here or anything. You just blow it up until the balloon doesn't move anymore. Then you're done. Okay, another example with gravity. With gravity, you're a bit more constrained. You need to have positive mean curvature, but in addition, your surface has to be a height field. You cannot sort of bulge out of, and get a surface that cannot hang. And here's the optimized linkage. This is what it looks like in 2D. Our very expertly fabricated 2D model. It's just laser cut triangles connected with ring binders, right? So don't ask about structural performance here. And then, we hang it up. The people are masked because this was for an anonymous paper submission. So it's not because, they're ashamed of their work. And here you see the structure. And again, the form is completely programmed into the 2D material. Right? There's nothing that guides this form other than the structure of the material. And again, you can see, you can get these negative curvature regions, these saddle points, and you can do interesting structures. Here's some more architectural examples. I like this one because Mars has a low pressure atmosphere. So if you want to build something, you need to pressurize it anyway. So why not blow the whole thing up, right, from one piece? And in fact, I'm very excited that I'll meet the people who did this today. Are they here? There you are. Okay. Oh, that's you. Okay, perfect. This is super cool. And it basically uses the same kind of auxetic pattern, right? So, of course, much more sophisticated than anything we did physically. Okay. Let me just, and this is just a side mention, I want to show you some other work in this area of deployable surfaces, but it's so new that I don't have much to show. These are examples we created 2 days ago. So we're looking into these deployable gridshells. The video is horrible. It's just a screen capture. So these are just, if anybody cares about deployable gridshells, I'd be happy to tell you more about it. Hopefully soon we'll have some real results. But it's basically a way to look at scissor-like linkages that you can deform into interesting shapes. We built a first physical prototype. It looks something like this. Again, not very expertly done, but I think it has a lot of potential. Okay. I'm going a bit faster to catch up with some time that we lost. But this would be a good time if you have some questions about that type of research, because I'm going to pivot to another topic. So you can also think more about questions and we'll discuss at the end. But if you have anything immediate, I'd be happy to answer some questions now. Now we go to the second part of the talk, and that has to do with light and form. So my background is in geometry, and I really deeply sort of care about three-dimensional structures and how they interact with our environment. And if you think about how light and form interact, there's many applications where people are using contraptions like this, for example, to transform light using geometry, right? So this is of course for energy production. You shape these mirrors so that you move the light or the energy where you want it. Similarly, in architecture, these are some contraptions that are built to bring daylight deep into buildings, right? So the idea is to move light around. But everyday objects move light around quite a bit. So if you have an object made out of glass or out of metal, it creates these really intricate patterns. And in computer graphics, we call these caustics. So here you see this simple little glass statue, and as you rotate it and shine a flashlight on it, it creates these very dynamic and fluctuating and really beautiful patterns. The same kind of thing you also see at the bottom of a swimming pool, right? When the sun hits it. It's because the geometry of the surface creates that pattern. And my research question here was to say, well, these patterns look really interesting, but they also look kind of random. What if I want to control them? So this is another example of the kind of inverse problems that we like to look at. What if if I know the shape of this glass, I can easily compute the shape of this caustic. That's some stuff that people did in graphics 20 years ago. But what about the inverse way? What if I say, I don't want this image, I want something else? What does the shape of the glass have to look like to draw that? So in order to study this, we have to understand, well, how can we transform light? So if I look at these light beams here, what if I want to move them over there? Well, I can't move the sun, but I can put a reflector somewhere, right? And then we have very simple physical laws that tell us, well, the incoming angle is equal to the outgoing angle. So if I know the geometry, I know where the light goes. And similarly for refraction, it's a little bit more complicated, but still very elementary. It's the geometry, once the material is defined, that determines where the light goes. And if you look at this more particularly, if I take a single ray of light and I want to move it from here to, say, over there, then I have to change the orientation of my surface such that this incoming angle equals outgoing angle is fulfilled, which in turn means I have to modify my geometry a little bit such that this surface normal is actually present in my object. So our goal was now to say, what if I take some incoming light, let's say sunlight, which is approximately parallel, and I want to change it into something else. I want to prescribe an arbitrary distribution. So for example, I take these rays and I want them to move so that I draw this letter A, for example. How can we do this? To study this problem, I'm going to take a little detour into optimization. So, has anybody heard of optimal transport? Some people, some nods? Okay. I'm going to show you a very simple example and then I'll explain how it relates to our problem. So imagine you have 4 blue points and I label them A to D. They're indistinguishable. They're something, some objects, let's say. And you have 4 orange points, there's something else. So for example, this might be beer and this might be bars, right? And you want to move the beer to the bars. Every bar needs beer, right? So you could say, okay, I ship my load of beer from A to 2, from B to 3, from C to 1, and from D to 4. So in this case, every blue dot needs to go to exactly 1 orange dot. So this is basically an assignment that you can make. Now, if you have some additional constraints, for example, you might not want to travel so far. So if you want to say, let's say I want to travel the least amount necessary, right? And if you want to find the assignment among all the possible ones that minimizes that cost, that's called an optimal transport. So obviously this is not a good one, right? You would not move this beer to bar 2. You have a closer place to go. In this case, the optimal assignment maybe looks like this. Okay? So the question is, how can you find that? The problem is that if you try out all combinations, you have this problem of combinatorial explosion, right? So it's n factorial. If you have 4 barrels of beer and 4 bars, it's manageable. There's 24 different variants. If you have 8, it's 40,000. If you have 16, it's whatever that number is, right? So you cannot deal with these kind of problems in a naive way. Now, obviously, when you look at this, you would never send this thing to bar number 2. It doesn't make any sense. There's a lot of geometric structure in this type of problem. And if you exploit that structure, you can go down to algorithms that have cubic complexity. But that's still too slow for large problems. The kind of problem that we're looking at is on the order of 1 million barrels of beer, right? A lot of beer, a lot of bars. So we need faster solutions. And fortunately, faster solutions exist. So there's a lot of research that's been going on that we will leverage. But let me first explain why our problem is an instance of this type of optimization. What we're trying to achieve to do with beer and bars. So our goal is to take a light source, it could be the sun, it could be a flashlight, take some object that interacts with this light, let's say a glass plate, and manipulate it in such a way that I don't get, this boring image over there, but maybe I get something that looks like Albert Einstein. Okay? Can I find an object made out of glass or some other optically active material that can achieve that? Okay? And what's very important when you do this is that we want to make sure this is physically possible, right? And I can only bend light so much. So one way to encode that is to say I want to deform that surface in a minimal way. I don't want to unnecessarily bend light if I don't need to. And this turns this into an optimal transport problem. So I want to move this light distribution to that one by moving rays around, but in a way that doesn't do unnecessary work. The more I need to move light, the less likely it becomes that it's physically possible, right? Refraction is limited in what you can do. Okay, now the actual algorithm, I'm not going to explain in too much detail. Again, if you're interested, I'm happy to go much deeper. But the key point is that, well, first of all, what you have to do is you have to simplify, okay? We're not going to do Albert Einstein as a continuous function. We're going to do Albert Einstein as a bunch of dots. Okay, this is not Albert Einstein. It's just a bunch of dots. But the point is that if you move a continuous function into a discrete point cloud, there is a theorem that says that an optimal transport exists. This is actually not obvious that you can have an optimal solution, right? It really requires a number of assumptions. But what's even better is that this transport plan is a minimum of a convex function, okay? Which means that now we're in a much simpler setup than we are before, where we had a highly nonlinear non-convex function. Here we have a convex function, so I can do gradient descent, right? I can just do gradient descent and flow to the minimum, and I'm guaranteed that that's a global minimum, because the function, the energy is convex. Okay? So back to Albert Einstein, what do? We discretize it with a geometric structure called the power diagram. This is a variant of the Voronoi diagram that many of you might know. And the way to look at this is to say that you have these little points. These are my Voronoi sites. And the cells around them correspond to equal amounts of light energy. Okay? So the dark cells are big and the bright cells are small. And similarly over here. And this implementation of discrete optimal transport transforms these two into each other. So here's what it looks like. This is what I start with. And this is a very low resolution example so you can see what's going on. So each cell you can think of as one unit of light. And then if we do gradient descent, the whole thing evolves. And you can see at this low resolution Einstein emerging. You see the dark regions around the eyes become bigger, other things become smaller. And once gradient descent stops, you're at your solution. Well, you're at half of your solution, because what we found with this optimal transport is we now know where each light ray needs to go. And that in turn, through Snell's law of refraction, tells us what the surface normal looks like at each point. Right? So we found the normals of our surface, but now we have to integrate these normals to actually get a 3D surface. And this is a tricky part, because if you take an arbitrary field of normals, the chances are very low that this field is integrable, that it can actually be converted to a physical surface. But there are some theory that says that in the context of optimal transport, you get at least very close to an integrable field. And then we run another 3D global optimization on top of that to find the surface. And guess what? Of course. All right, good. So now back to Einstein. I brought Einstein. This is Einstein. So this is a surface that we've computed now with our algorithm. If you look at it, it's flat on one side. Now would be a good time to dim the light, yes. So it's flat on one side and it's curved on the other. And if you look through it, I don't know if you see that, it distorts quite heavily, right? But if you look closely, and I'll pass it around in a second, you don't see anything in terms of geometric structure. So if you dim the light, I think it will be easier to see. I can actually probably use the projector. So here you see as I don't know if you can see it. Let me try something else. I don't know if this will work with the mic. Hands-free. So I can also try to, I mean, it's actually calculated for parallel light like the sun at 20 centimeter distance from the wall. So something like, or 30 centimeters, this would be pretty much optimal. But you know, you can project it a little bit larger as well. You have to find sort of the right distance to make it work. Okay? So that's Einstein. The other example, I don't know if anybody can still hear me with this thing. It's a bit tricky to hold the microphone. Is this brain model. And actually, maybe I'll just use the projector. What you see here, what's interesting, and the same is true for the Einstein, if you look at the lower parts, it's completely black. Right? It's as black as the shadow of my hand. So really no light is going to the lower parts. All the light is being projected into this drawing of the brain, which is much brighter than the ambient light of the projector. Right? So we're really focusing heavily the light. And it's a little bit sort of counterintuitive at first because the object, of course, is completely transparent, yet it can create a completely black shadow. Right? But of course, we're just moving light around. Okay? I'll pass that around. Actually, I'll pass those around now. You can also play with your iPhone or whatever flashlight you have on your phone. Please don't touch the actual surface. Try to hold it at the bottom or on the side because it scratches quite easily. All right. That was the brain. You can also do color. This is very simple because we know exactly where the light comes from, so we can just add a color foil to the surface and then get these kind of colored images. I actually most like this in the sun. So if it's sunny outside, we can later have a look. I think there's a little part in the video at the end. It really works very nicely with the sun, and the sun is, of course, much more intense, so you can, you get a lot of brightness. To make the caustic work, you have to get the right distance, right? So you have to play with it. Both of those have a distance of roughly 30 to 40 centimeters for parallel light, which is hard to do with your flashlight. Right? Maybe, oh no, I need this for one more. Then I pass it around. Here's another example. This is the kind of resolution you can get. Right? So this piece is about that big. It's like a little pendant. And it has been produced with an optical milling machine. You can do the same in reflection. I have one reflective example here, which maybe I'll just pass that around. You can play with it. It's been a little bit scratched, so might have some issues. But it's basically this model here. And we try to scale this up a little bit into architectural dimension. This is the Rolex Learning Center. What you see here are 4 metal plates of 1 by 1 meter each that reflect the sunlight onto this concrete roof. And of course, it depends on the time of the day and the time of the year. So these have been spaced out that at different times of the day and different times of the year, they draw these images. If you go to the website that's up there, you'll find time lapses and see how things change. Now in the winter time, it actually gets really interesting. you can't distinguish these faces anymore. It becomes just abstract light art. So come visit us in Lausanne if you want to see something like this. Come between May and September on a sunny day, of course. Doesn't work without the sun. And then we also did, I show you one other example. This was an art exhibition with Pierre Soulages, where we created some interactive installations where people walked around with flashlight like the one I'm passing around to do some interesting interactive exploration around light. If we have time later, I can show you a video. It's easier to understand. But maybe in the interest of time, let me conclude now. So if I want to describe generally how we work, then we're just kids, right? We play. So the first thing of every research project is to gain intuition, right? We had this thing, I was playing with this for hours, deforming it. At some point it got destroyed. Just to understand, what is that? What could it be? And the same with the light. You just play with a glass of wine in a restaurant, and you see these patterns, and you're like, what is that? And then the next step, and that's already a hard step, formalize the problem. Right? What is it that you're actually trying to study? Well, okay, there are several steps in between that I should mention. You first try to abstract and model in a precise and mathematical way what you're actually studying. Right? So you have to look at the laws of reflection. Here you have to look at these material properties. And then map it into a mathematical representation that can allow you to leverage what many, many people have done before you. Right? In this case, like these theorems we didn't prove. We proved some others, but this was well-known mathematical theory that helped us a lot to understand the problem. And if you get that understanding, in particular, if you can answer questions of what's possible and what's not possible, or how do you have to tweak the problem to make something possible, right? Then you can define efficient, stable, and successful algorithms, right? Using optimization as a black box almost never works. If you don't understand the geometric structure of your problem, just throwing a solver at it, in my experience, is not something that is, it can be successful, but if you have complicated problems like the ones I showed you here, this is very hard. And then, of course, you need to validate what you did, and now we're much more going towards, building physical prototypes to see that the whole theory and all these idealizations and abstractions make sense. And in fact, building these prototypes helps us in our intuition, and then the cycle sort of continues. It looks very linear right now, right? That's not how we arrive at this. This is the cleaned up version after, 2 years of pain. But this to me is the essence of computational design. If you want to really leverage algorithms and data and computation, then you need all of these things, right? You need a solid theoretical foundation. You need strong algorithms, but you also need to, have the intuition and validate what you do in the real world. And before I stop, I want to thank the people who worked with me on this. These are the main people, but of course also Philippe here. He was there at the beginning of our caustic research that has evolved quite a bit. And he was actually responsible for us pushing it back into the physical world. At the time, we only did simulations, but Philip said, we have to build something. Thank you for that. Okay, with that, I want to conclude, and I'm very happy if you have any questions or want to see more things. But thank you for your attention.